The last part in conjugated systems is Diels-Alder reactions, a very specific class of name reactions, just like we did Grignard's. Here is Diels-Alder. So Diels-Alder were actually two scientists, two chemists who got the Nobel Prize in 1950 for this reaction. It's a very neat reaction, very simple reaction, easy to do reaction, and gives great product. Okay, so what it does is it takes a diene and combines it with an alkene. So a diene is also an alkene, it's two double bonds with plus one double bond. And what it does, it forms a ring as a product. Okay, so here is an example of a reaction where you have a diene which looks like this. Okay, so here is the conjugated system. Now remember, it has to be conjugated. Okay, it has to be alternate double bonds. It can't be isolated. And so here is the diene, and then here is an alkene system. And when you heat these two together, they end up giving this compound, which is now a ring structure, which we did not have a ring before, but now we do. So this over here, the first compound here, the one with the double bonds, the two double bonds, is called a diene because it has the two double bonds. And the one with the one double bond, or this could be anything, it could also be a triple bond, but anyhow, this is called the dienophile. And finally, the product is called the adduct. Okay, and typically you will have a cyclohexene ring over here because you have a 6 electron system, okay, reacting over here. These arrows here kind of tells you again about the concerted mechanism. We talked about the concerted mechanism back when we were trying to form epoxides. And so in epoxides also you have a concerted mechanism, and here also. So which means there is no clear start of arrow, or which is the first one, which is the last one, you don't know. Okay, so anyhow, it's a neat reaction, and all you need is heat and maybe some solvent, like a non-polar solvent like benzene or toluene or hexane, and boom, this reaction is done. So examples of Diels-Alder reaction, there essentially are many reactions that you can do with Diels-Alder, okay? But just to get us started, here is a diene, okay, where you have these two double bonds, and again, you can have substituents on this. We will talk about the substituents on dienes. And then here is a dienophile where you have a double bond here and a triple bond over here. And so once this diene combines with this alkene over here, this is the structure that you get. The nice thing about these reactions here is that they're all color coded, so you can see what fragment is coming from the diene and what fragment is coming from the dienophile. So the dienophile is the green one, okay, that's over here. So the interesting thing is, if you look closely, of course, is that there are 3 new bonds formed, okay, over here. The one new bond formed is here, which is this one. The other new bond formed is this one, which is this one over here. Okay, because remember, this is your diene. Okay, so this is a new bond formed, and this double bond is also a new bond formed because we didn't have a double bond here before. So during the mechanism, the electrons got shifted around, and so the electron shifted from this double bond here to form a new bond over here. The double bond shifted from there to here to form a new bond, and then this double bond electrons shifted from here to here to form a new bond. Okay, so that's how you get 1, 2, 3 new bonds, okay, in here. So anyhow, one thing also I want to point out to you, that you end up getting a cyclic structure at the end, which we mentioned before also. But if there is no ring in the diene or the dienophile, you get only one cyclohexene ring, okay, in the product. However, you can also make bicyclic compounds, okay, using Diels-Alder reactions. And in this case, you start with a ring structure. So either the ring structure is in your diene or in your dienophile. In this case, it's in the diene. And so again, you look at where your double bonds are, and right here are your double bonds. So at the starting point of this and here, okay, where your double bonds start, that's where you form the new bonds. So one here and one here, okay? And look at the structure over here. This is also not even an alkene, this is an alkyne. So you can have an alkene or an alkyne as your dienophile. And so the new bonds that are formed are right here and here, and then in between the two double bonds here, okay, between the conjugated system. So that's where we have here the new bond right here, here, and then here is another new bond. This carbon over here has shifted up over here. Okay, and this is a bicyclic system with one ring over here, and one ring is the blue one that was the original ring. Okay, and the new ring that you have formed is of course the cyclohexene ring. You will always form a cyclohexene ring because you will always have a 6-pi system. Okay, so you will always have a cyclohexene ring. The other ring will depend on what you started with. So again, here is the dienes, here are the dienophiles, and then here are the adducts that you will form. You will have to go forward as well as backward for me. Okay, so which means I can give you a product, and then you will have to tell me what is the diene and the dienophile that were required to make that adduct. We'll practice that in class. So the mechanism, as we say, is concerted mechanism, which means there is no clear nucleophile or electrophile. You don't know where it gets started. You just know that here is an arrow, here is an arrow, here is an arrow, wherever, somewhere. But anyhow, all of this gets overlapped, and then you end up forming a ring. Okay, and then here is the ring, here are the extra electrons that are left over. So that's the new bond that's formed. In looking at it from an orbital point of view, from molecular orbital point of view, here are the double bonds, which is the pi bond here, the pi bond over here, and here's also a pi bond in the double bond in the alkene. And so you end up forming overlaps between here, overlaps over here, and then overlap here. And once you have those overlaps, see those? Okay, those are the new overlaps that are happening. And once you have those overlaps, you end up forming the new structure. Okay, so the mechanism is concerted. All right, so traditionally nobody asks for the mechanism for Diels-Alder reactions. However, it's kind of nice to know so that nobody tricks you into thinking that there is an electrophile or a nucleophile. However, in general, we call this the more electron-rich species. So this is called the nucleophile, and this is considered to be the electrophile because this has less electrons in it. So the dienes and the dienophiles. So let's go over this a little bit more. Okay, this was the original reaction that we saw on the first slide. So here we have the diene, okay, with the 2 electrons. So this is considered to be the electron-rich species, which means that this would be considered a nucleophile. Okay, even though you don't want to call it a nucleophile, but it can be considered as a nucleophile. And here is the dienophile, which would be then considered to be the electron poor species, and so the electrophile. You have to have some sort of an imbalance of electrons, otherwise the reaction is not going to take place. It has no motivation to go forward. Okay, so some of the properties of diene and dienophile, okay, they're listed over here. So the diene is the diene component, which means it's the double bond. It is also the electron-rich component, whereas the dienophile is more effective if it is electron-poor component, okay, of the reactions. So which means that if the diene, which has the 2 double bonds, you make it richer in electron, it becomes a stronger nucleophile. Essentially, that's all you're doing to it. So which means that you can add groups to the diene to make it more electron-rich, and then you can add groups to dienophile to make it more electron poor. So which means that you're trying to make your reaction be a little bit more better, for the lack of a better word, okay, but you're trying to make it more efficient. Okay, so by making your diene more electron rich and the dienophile more electron poor. Okay, so that is what makes the reaction go forward even more. So what are these? So in case of dienes, you want something that are electron donating groups or electron releasing groups, and for dienophiles, you want something that is electron withdrawing groups. Don't look over here. Look at this table over here first. Some of the electron donating groups are alkyl groups, and you've learned that before also in Organic 1, that all alkyl groups or any kind of aromatic groups also, like a phenyl group, for example, those would be considered electron donating groups. So any alkyl groups, okay, would be considered electron donating groups. Ethers, okay, where you have the oxygen directly connected to the double bond, would be considered as a good electron donating group. Okay, this kind of an ester where the oxygen is directly connected to the double bond is considered to be an electron donating group. All right. So what happens with these two over here is that the electrons from the oxygen, the lone pair of electrons from the oxygen, tend to delocalize over the electrons of the pi bonds in the diene. Okay, and so they end up making it more electron rich. Okay, so there is delocalization effect going on. With the dienophiles, you want more electron withdrawing groups. Okay, so in the electron withdrawing groups, you will find that there is no direct connection of oxygen with the double bond. Okay, so with the alkene now. So all these species, they all have oxygen, because traditionally we know from Gen Chem also that oxygens and nitrogens and some halides, they are very electron withdrawing groups. These are all electronegative groups. So if they're electron negative groups, they are going to be electron withdrawing groups. So that's why ether is a little bit unusual, because oxygen here is electron withdrawing group. However, because it is directly connected to the double bond, the lone pair of electrons can delocalize over the double bond. However, in these cases here for the dienophiles, where you have the electron withdrawing groups, which also have oxygens, in these cases, the oxygens are not directly connected to the double bond. Okay, and so therefore they become very good electron withdrawing groups. I want you to look at the ester here. Okay, and there was an ester here also in the electron donating groups. So the ester here in the donating is connected a little bit differently than the ester over here. So the ester in electron donating, it connected to the double bond by oxygen, whereas here it's connected by carbon. All right, so that prevents the delocalization of the lone pair of electrons. So these are the electron withdrawing groups over here: aldehydes, ketones, carboxylic acids, esters, nitro group, cyano groups, and you can also have fluorine in here, because fluorine is a very electronegative group. Some of the other halides though will fall over here, because halides also have lone pair of electrons. So bromine and iodine will be more electron releasing than electron withdrawing. I want you to keep this chart handy, because this one is a very key chart which we will use later on also. Okay, so this will become a very important chart for you. It's not just for this chapter, it's also going to be used later on. So here are some other dienophiles. So look at some of these dienophiles. This is how it will be attached. Here is a very common dienophile where you have one double bond. However, you can make it more effective if you add an aldehyde. So this is how it is added. So when we're talking about adding an electron withdrawing group, this is how you would add it. Okay, so here is an ester group that is added. Here is the nitrile group or the cyano group that has been added. Okay, and so if you have two carbonyl groups, that makes it even better of a dienophile. So the more electron poor you make a dienophile, the better it is. Okay, and again, this is a very typical question that you will get in any kind of an exam or assignment, is you'd be given a series of compounds where you have to decide which one is the better diene or dienophile. One of the interesting aspects about Diels-Alder reactions is the stereospecificity. Okay, and the stereospecificity means that you can get a very special or specific stereo compound. Stereo compounds means R and S, or cis or trans. So here we have the butadiene, okay, just as usual. But here are two isomers of butanoate. Okay, so here is your diene. Here is the diene, here is the dienophile. So here is the double bond, here is the double bond. But the only difference between these two compounds here is that one of them is E, one is Z, or one of them is cis and one of them is trans. So this is the cis alkene or the dienophile, and here is the trans dienophile. And then look at the products that you end up forming. So depending on how the diene and the dienophile approach each other, this is what you will form. Okay, and then here also, here in this case, when you have the E approaching, then now you will form the trans, because originally the hydrogens were trans to each other, so you'll end up forming a trans product. And this is something you have to be aware of, because alkenes can have cis and trans bonds. So if the cis and trans is shown to you in the dienophile, then you please make sure that your product also has that stereochemistry shown in there. Now you get this product, which is a cis product here, but you also get the enantiomer for this, okay, in which both of these hydrogens are going back. In some cases, you have symmetry, and so it doesn't really matter if you have enantiomers, because then you'll have a meso compound. But in some cases, this matters because you will have two products in the end, this compound and then the mirror image of it. Okay, and then here also you will end up getting two compounds, this one and then the mirror image of it. You don't really have to write both of them, but you just need to know that you are forming both the enantiomers. Okay, so again, if you have cis dienophile, you will get a cis product. If you have trans, you will get a trans product. Another interesting thing about Diels-Alder reaction is regioselectivity. Stereospecificity has to do with getting a specific stereoisomer, RS or ZE, those kind. But regioselectivity has to do with how these two approach each other and then which one is going to be the more stable product. Okay, and so in stereospecificity, you don't really have that option. Okay, because if you get one enantiomer, you will get the other one. There is no stability conditions in there, but regioselectivity gives you stability problems. Okay, and so here we have maleic anhydride, which is the dienophile, and here is the diene, which is cyclopentadiene. And there are two ways that the maleic anhydride can approach the cyclopentadiene. Okay, this is one approach and here is one. So let's look at it one by one. Here in this case, the dienophile here is directly underneath the cyclopentadiene. Okay, and so once the bonds form, you end up getting an endo product. Okay, however, in this case, the dienophile, the maleic anhydride, is actually facing outside, and so you end up forming an exo product. Okay, now the key thing over here for looking at the regioselectivity is not only for the fact that you got the endo product which is facing down, or the exo product which is actually going up, okay, in a way, but it really has to do with steric hindrance. Okay, which one is more sterically hindered? And usually we are thinking about cyclohexane rings back from conformation analysis, and we tend to think that, well, this one would be more stable because this is going outside. However, what we have to look at is what else is it interacting with. Okay, and here actually it's interacting with this carbon and whatever group is on it. So the exo products actually are a little bit less stable because there is steric hindrance. On the other hand, with the endo product, there is plenty of room over here, so there's nothing that it can interact with. So there is no steric hindrance, so which means that endo products usually will be a little bit more stable than the exo products. Okay, again, exo have steric hindrance with this carbon over here and then these bonds coming up. Okay. The last aspect, or one of the last aspects about this reaction is the conformation of the diene. Okay, so we've talked about the dienophile and how it approaches and the fact that the diene can be cis and trans, but let's look at the diene for a change. So here is your diene, which is butadiene, and this is how we have been writing it, okay, that this is what the diene is. But you can have rotation around a single bond. Double bonds don't rotate, but the single bonds can rotate, all right? Which means that this is one conformation possible of a diene. And then here is another conformation possible of a diene where the double bonds are actually in opposite locations, okay, or in opposite places. So here they're on the same side and here they're on the opposite side. Now, for the lack of better words, this is called S-cis and this is called S-trans, even though we all know that cis and trans is limited to double bonds, not single bonds, but we're actually looking at the conformation of how these double bonds are related to each other. So the double bonds here are on the same side, so it's called cis, and the double bonds here are located on the opposite side, so it's called trans. Okay, and so are these two the same then? So will both of these undergo Diels-Alder reactions or not? And the answer to that question is that only this one is going to undergo Diels-Alder reaction. This one does not undergo Diels-Alder reaction. And the reason for that is that here you have all the orbitals. Remember we talked about double bonds having p orbitals because they have the pi bond. So here we have the orbitals, here we have the orbital, and then here also we have the two orbitals which can then directly overlap with the orbitals on this double bond. And this is when you have the cis conformation. But when you have the trans conformation and the double bonds are far away from each other, it is really very hard for the dienophile to overlap with both of these orbitals at the same time. Okay, so then um, the trans conformation does not react. Okay, now in this case, this is not even an issue because single bonds rotate. So why would butadiene stay in this conformation? Well, it won't. Okay, and so eventually it will actually come to this conformation for the reaction. However, in some cases, this kind of a double bond is locked and you cannot have any kind of rotation. So for example, if I were to draw 2 more carbons over here or 3 more carbons here and lock it into a ring, now as soon as I have a ring, I cannot rotate this double bond anymore. And so now these double bonds are locked into position, and if they're locked into position, then that kind of a diene or a diene is not going to undergo Diels-Alder reaction. So look carefully at what kind of diene you have and whether it is stuck in a trans conformation. If it is stuck, then you cannot have Diels-Alder. However, if it rotates or if you can get it into a cis conformation, we're good to go. So this essentially is all about the Diels-Alder reactions. There is not much more to it. We'll practice a lot more in class where we write reactions and go back and forth and determine the strength of dienes and dienophiles and so on. But anyhow, I want you to know from this little portion is the dienes and the dienophile, how to classify them, what are the electron withdrawing groups and the donating groups, and how that makes the diene a better group or the dienophile a better group if it's attached to electron withdrawing groups. I want you to know the stereoselectivity of the Diels-Alder reaction, the regioselectivity of the Diels-Alder, and finally the conformation of the Diels-Alder reactions. Okay, and so go through all of that.